Hey everyone, welcome to this explainer. Today we're unpacking a pretty wild paradox in space history. We're looking at how the most powerful rocket humanity ever built taught NASA its absolutely most vital lessons, not by working flawlessly, but by failing spectacularly. Seriously, what actually happens when the biggest rocket ever built just fails mid-flight? Well, let's dive right in. To an outsider, this mission probably looked like a total disaster. But as you're going to see, it actually paved the way for one of our greatest lunar triumphs. We're talking about Apollo 6. This was the mission that took the mighty Saturn V, pushed it to its absolute limits, broke it, and literally saved the future of the Apollo program.
To wrap our heads around this, here's our roadmap. We'll start with the race to the moon, look at the purpose of Apollo 6, break down those 3 critical flight failures, check out the engineering fixes, and wrap up with the legacy of Apollo 6.
Part 1. The Race to the Moon. So, picture the late 1960s. The U.S. is pushing hard toward that audacious goal, landing humans on the moon and getting them back safely. The stakes? Unimaginably high. After the heartbreaking tragedy of Apollo 1, the uncrewed Apollo 4 mission was a huge win. It showed the rocket could work and restored some much-needed confidence. But here's the thing about aerospace engineering. One successful test just doesn't cut it when human lives are on the line. NASA had to know without a shadow of a doubt that the massive Saturn V was consistently reliable.
Part 2. The purpose of Apollo 6.
NASA definitely wasn't taking any shortcuts here. Apollo 6 was designed as the critical second uncrewed test, basically a full dress rehearsal. The goal was to push the system way further than Apollo 4 did. They needed to rigorously test the rocket stages, push those engines to the absolute brink, and subject the whole spacecraft to the brutal, intense stresses of launch and high-speed re-entry. Simply put, they needed absolute confirmation this beast of a vehicle was ready for humans.
Part 3. 3 critical flight failures.
Okay, so April 4th, 1968. The Saturn V lifts off with this ground-shaking power. And for a fleeting second, everything looks textbook. But as it climbs higher, a cascading sequence of sheer chaos unfolds. The mission was hit by 3 major technical failures right in a row. It was like a terrifying domino effect. Let's break down exactly what the hardware and the extremely stressed-out engineers on the ground were actually dealing with.
Failure number 1. Pogo oscillation. Basically, this is a violent vibration caused by the rocket engines interacting with the vehicle's structure. Imagine driving down the highway and your engine suddenly makes the entire car frame violently bounce and shake. That's pogo. These oscillations were way stronger than anyone anticipated, putting massive stress on the rocket and raising immediate, glaring red flags about what that kind of shaking would do to a human crew.
Somehow, despite those terrifying vibrations, the first stage held together and separated. But then, problem number 2 hits. Right in the middle of the second stage burn, exactly 2 out of the 5 critical engines just shut down, completely premature. This is a massive, massive failure, folks. Those engines were absolutely crucial to hitting the speeds they needed for the mission. But you know what's truly incredible here? It's how the rocket's internal logic handled the crisis. It showed unbelievable resilience. Because 2 engines died, the automated systems actually forced the remaining 3 to compensate by burning significantly longer than planned. It adapted to a major hardware failure in real time. Now sure, it kept the rocket ascending, but it introduced a whole new level of extreme stress and uncertainty into the flight profile. So the rocket limps into Earth orbit. And then, a third blow. To simulate the trajectory to the moon, the third stage engine needed to pull off a high-energy restart. And nothing. It completely failed to ignite. This meant they couldn't simulate the full lunar trajectory at all. NASA flight controllers had to scramble and adapt on the fly, using whatever capability the spacecraft had left just to salvage the mission and scrape together some high-speed re-entry data.
Part 4. Fixing the Saturn V. Amazingly enough, the command module actually survived a modified, high-stress re-entry and got scooped up from the ocean. But these incredibly mixed results shifted an immense amount of pressure straight onto the NASA engineers. They had a rocket that could technically survive its own failures, sure, but those glaring flaws had to be completely eradicated. They didn't just patch things up, they aggressively attacked the data. They traced the engine shutdowns to faulty fuel lines and pushed through rapid design changes. They built structural solutions to dampen those violent pogo vibrations, and they immediately fixed the ignition mechanisms for that restart failure. Every single issue had to be definitively resolved. There was zero margin for error.
Part 5. The legacy of Apollo 6.
Because the engineers dug in, understood, and actually solved these deep-seated problems, NASA made a staggering decision. They trusted the fixes
and move forward with crewed missions. The pace here is just mind-blowing. Apollo 6 flew in April 1968. By December, yes, that same year, Apollo 8 used that exact same Saturn V design to take astronauts all the way around the moon. And by July 1969, humanity was walking on the lunar surface. None of those triumphs would have happened without the brutal lessons of Apollo 6.
This really highlights a fundamental truth of aerospace engineering. Look, simulations and theoretical models are fantastic, and they're obviously essential, but they can only take you so far. It's only through actual real-world flight tests that you expose the hidden fatal flaws in complex systems. Things like pogo oscillation and ruptured fuel lines, those only reveal themselves when you actually light the candle and face the brutal reality of physics.
So ultimately, Apollo 6 wasn't a failure at all. Honestly, it was a vital, necessary stress test. It caught fatal flaws before human beings were ever strapped inside. It absorbed those failures so that the astronauts of Apollo 8, 9, 10, and 11 wouldn't have to. It's engineering adaptation at its absolute finest.
As we wrap up this explainer, I want to leave you with this. When we look to the future, to new rockets returning to the moon, and eventual crewed missions to Mars, we really have to ask ourselves, are we prepared to accept that our greatest failures are often the essential stepping stones to our greatest achievements? Will we keep embracing the productive failures that make ultimate success possible? It's a crucial mindset for exploration. Think about that as we keep pushing the boundaries of what's possible out there. Thanks for joining me. Keep asking questions, and I'll catch you on the next one.